So, good morning students. In the previous class we had seen the modeling of the interface elements, and in today's class let us look at how we can model the semi-infinite nature of the soil, because as you know the soil is a semi-infinite in extent. Wherever you go there is soil. Then how do we accommodate that in our analysis, because we are basically doing finite element analysis with some finite domain like finite length and finite height and so on. But then how do we represent the semi-infinite nature, and that is what we are going to see in today's class. So, when we deal with many of the geotechnical problems, we come across this type of integrals, integral of function integrated from minus infinity to plus infinity, 0 to infinity and so on. So, when we do this analytically, we can easily handle, but then the moment you mention the word infinity to any numerical program, then they get jittery, they will just simply collapse, they will say that no, we give up. And so, we need to find some other way, and we cannot really substitute any infinity in any of our parameters, whether it is the Young's modulus or the limits and so on. Okay. So, our the analytical solutions that we have seen, they can consider, we might have derived several solutions in the elasticity, and also even in within the geotechnical engineering we deal with so many things, but cannot do them numerically. And the boundary element method, that's actually it is not similar to finite element, but it's another numerical method where we consider the boundary and we can represent either the outside of the boundary or inside of the boundary, and we can apply these boundary element methods, because if you say outside of your boundary everything up to infinity, that is automatically considered in the analysis. Or some people they consider the finite element analysis, but then prescribe some known displacements along the boundary. These could be from your theory of elasticity solutions, and by prescribing these known displacements at the boundary, we may be able to partially account for semi-infinite nature of the soil. But then this may not be practicable in all the problems. Maybe in some cases we can get the solution, but we cannot do that in all the cases. And some investigators they tried combining finite elements and then the boundary elements, because the boundary elements are good in representing the boundary problems, and the finite elements are good within the finite region. And so, when we deal with any dynamics problems, the boundary plays a very important role. So, if you place the boundary too far, then your computational effort could be very high, because instead of having let us say 1000 degrees of freedom, you may be having 10,000 degrees of freedom, because you have additional number of elements. But if you place the boundary too close, also you will have a problem, you will have some numerical influence, like your waves may be propagating. Once they reach the rigid end, they will reflect back, and then your oncoming wave and the reflected wave might interact, and they might produce some other extraneous stress condition within the soil, and that is also not correct. See, one simple example that I can give you about the reflected wave is, so when you have a driven pile, you know that you are giving energy at the top, and if the soil is strong enough, it will absorb the energy, and then it will allow if the energy that you are imparting to the pile is much higher than the resistance, then the pile will be driven into the soil. And if you are So, when you are driving and you give a large energy and suddenly let us say you come into a soft clay, and the soft clay obviously it will not be able to absorb the energy that is coming from the pile. So, it will get reflected back, then that will reflect in the tensile stresses generated. So, if your waves are moving apart, like let us say oncoming wave and then the reflected wave, if they move apart, they will produce tension. And so, if you see the IS code for the driven piles, they recommend a very large percentage of steel, almost 2% of the cross section, whereas for a bored pile it could be just a nominal reinforcement for the normal shrinkage purposes. So, this additional steel in the concrete of the driven piles is because of these extraneous stresses that you could generate. And the same thing happens even in the case of finite element analysis of our geotechnical problems. And so, we need to take the boundary very far away, and to overcome that, now we have these map type infinite elements that can represent infinite soil medium by using one simple element, okay, that we will see in this class today. And just to illustrate, I have a small problem, like let us say we have a dam and that is resting on the soil, and then we are giving some seismic excitation, and there are some moving boundaries or viscous boundaries, and let us monitor the deformations at this point A, very close to the dam, and these are all the results that we get by locating the boundary at different locations. The green line is when your boundary is at a far off location, and then the blue, red, and then this pink line, they are all with different distances, and you see your numerical result does not like it not only depends on your properties, but also on the boundaries. So, if you place the boundaries too close, then your displacements are very high, and as you move the boundaries far away, then the result may be more appropriate corresponding to the loading. Whereas with boundaries too close, your results may be affected by oncoming wave and then the reflected wave. So, because of this, you need to be very careful whenever we are doing this type of dynamics problems where we have some wave propagation. We need to do something, and one method is by providing absorbing boundaries, but absorbing boundaries also may not be effective in some cases. So, we can go in for these infinite elements that can represent the infinite soil medium. So, in the recent past, almost about 40 years, varieties of infinite elements have been developed. Some are based on including infinite soil domain in the analysis. We can define with very large displacement, or the distance, and we can prescribe some known solutions at some finite distance, so that we can represent the infinity, or we can combine boundary element and finite element. And then the more recently map type infinite elements, and these elements are very simple, and also these are also isoparametric. So, they are compatible with the other finite elements that we have developed. So, they are easy to implement, and then we do not need to do much changes in the existing computer programs to implement these map type infinite elements. See, these are all some of the papers you can go through for some literature on the infinite elements, and of course, there are many more number of papers that I did not list here, but I have just listed some more some very prominent papers. Let us look at one dimensional mapped infinite element to start with, because that is the simplest one. And let us take a 3 node bar element, an axial element with the 2 nodes at some finite distances x1 and x2, and let us say the third node is at infinite distance. Okay. x1 and x2, these are the finitely located nodes, and then x3 is at infinite distance. This is the Cartesian space, but then the corresponding isoparametric element will be only in the space of -1 to +1. So, we have 3 nodes, one at xi of -1 at 0 and xi of +1, and the node at xi of +1 is the one at infinite distance. And so, how do we simulate that in our numerical analysis? So, we can actually develop some mapping functions that are singular at xi of +1, and we can do the mapping in terms of these 2 nodes that are located at finite distances. So, when we develop our polynomial equations, we can develop them with a singularity at xi of +1, so that we can represent the infinite distance at the third node, and this singularity we can achieve by having in the denominator 1 minus xi or 1 minus xi whole square or square root of 1 minus xi or square root of 1 minus xi square and so on, like there could be anything, like any combination, such that when xi is +1 you should have singularity, that is you should have 0 in the denominator, so that the value will blow up, it will go up to infinity. And one of the simplest ones is by using a polynomial like this. Let us say you have 2 finitely located nodes at x1 and x2, and we can write the x as a function of a0 and a1. These are the generalized coordinates, a0 by 1 minus xi plus a1 by 1 minus xi times xi. Okay. And purposely we had made them singular at xi of +1 because we want infinity. Okay. And we can determine a0 and a1 in the same manner as how we determined them earlier, by substituting xi of -1, our x is x1, and at xi of 0 our x is x2. So, by going through we get that a0 is x2. Okay, that is when you substitute xi of 0, our x is simply a0, that is equal to x2, a0 is x2, and then we see that a1 is x2 minus 2x1, and our x of xi we can write as x2, that is a0 by 1 minus xi plus x2 minus 2x1 by 1 minus xi times xi, and by grouping these under x1 and x2 we can get this m1 can be written as minus 2 xi by 1 minus xi, and m2 can be written as 1 plus xi by 1 minus xi, and we can write our x as m1 x1 plus m2 x2, where m1 and m2 are our mapping functions, and our m1 is minus 2 xi by 1 minus xi, and m2 is 1 plus xi by 1 minus xi, and if we sum up these two mapping functions we get exactly 1, and m1 plus m2 of 1 means there is a unique mapping between the Cartesian space and then the isoparametric space. Okay. And and then at xi of +1 we have infinite distance. Okay. And let us calculate the dou x by dou xi, that is our Jacobian determinant for the one dimensional problems, and that is equal to dou m1 by dou xi x1 plus dou m2 by dou xi x2, and that is 2 times x2 minus x1 by 1 minus xi whole square. And for finite element we have seen that the dou x by dou xi is equal to the half the length. Okay. For bar element of some length L, the dou x by dou xi is just simply L by 2. Okay. So, at different xi values, let us calculate this dou x by dou xi. At minus 1, it is 0.5 times x2 minus x1, okay, and at minus of square root of 0.6, it is 0.635 times x2 minus x1. See, these are all the sampling points that we have with 2 points and then the 3 points. At 0, it's 2 times x2 minus x1, and at plus 1 by root 3, it is this, and at plus of square root of 0.6 is about 39 times x2 minus x1. And actually, although we have the singularity at xi of plus 1, we will not have any numerical problems, because we are not going to use any sampling point at xi of plus 1, and we are also not going to compute any stresses or the strains at xi of plus 1. So, we should not have any technical issues by using this type of singular mapping functions. And as we see here, as xi is tending towards 1, our Jacobian value is increasing rapidly, and in fact exponentially beyond xi of 0. So, that means that our mapping functions with singularity in the mapping functions, they are able to represent semi-infinite domain. Thus, the Jacobian value is in the denominator. When our integral B transpose dB calculations are done, our determinant of the Jacobian is in the denominator. So, in fact, when you calculate the stiffness of any stiffness matrix of an infinite element, we will see that it is of a very small value, because your determinant of the Jacobian matrix is in the denominator. And so, for doing the finite element calculations, we can use the normal shape functions for interpolation. So, for interpolation of displacements or the pore pressures, we can use the normal shape functions, and then for forming the B matrix, we can use the singular mapping functions. And then, as the third node is at infinite distance, the nodal variables like your displacement, strain, stress, and the pore pressure, everything will be 0. And so, we do not really need to do any interpolation based on that value. Okay. And our interpolation for the field values is N1 U1 plus N2 U2 plus N3 U3, where our N1, N2 and N3, they are our well known shape functions that we have derived for the isoparametric elements. And then in this case, our U3 is 0. So, in fact, we may not be including this in our interpolation. The reason is because your U3 is anyway 0, and our N1 is xi times xi minus 1 by 2, N2 is 1 minus xi square, N3 is xi times xi plus 1 by 2. And in this case, the shape of mapping functions are not the same. We have two different sets of functions. See, the mapping functions are minus 2 xi by 1 minus xi, or 1 plus xi by 1 minus xi, whereas our shape functions are xi times xi minus 1 by 2 and 1 minus xi square, and so on, because we have basically 3 nodes for interpolation and only 2 nodes for the mapping, and that too for the mapping we have singular mapping functions, whereas the interpolation is done by using our conventional interpolation functions. So, in this particular case, our mapping functions are linear functions, because we have used only 2 nodes for our mapping, whereas we used 3 nodes for interpolation. So, we have the quadratic functions, quadratic shape functions, and linear mapping functions. So, these mapped infinite elements, they belong to the category of subparametric elements, in which the interpolation functions are of higher order compared to the mapping functions. See, in the first class on the isoparametric elements, we had seen 3 types of elements: isoparametric, in which both the mapping and shape functions are exactly the same, and then the superparametric, where the mapping functions are of higher order compared to the shape functions, and then subparametric, where our shape functions are of higher order compared to the mapping functions. So, our infinite elements, they belong to this subparametric category. And then another thing that we need to notice is, when we had discussed the convergence principles, one of the requirements is that our mapping and shape functions should be well defined at all the nodes within the element. And but in this case, our mapping functions have singularity at xi of +1. So, we are not really satisfying all the requirements of the convergence, but then our sigma of m is 1. So, that means that we can get unique mapping, and in general, once you have the unique mapping, that means that you can get the convergence also, because our sigma of ni is 1, because we are using the conventional shape functions. So, here and we dealt with x1 and x2 and infinity, and should there be any relation between the x2 and x1? Let us see whether there needs to be anything. See, where should we locate x2 with respect to x1? This is our general equation for x in terms of xi and x1 and x2. Let us substitute x2 as 2x1, and so our x of xi is 2x1 by 1 minus xi, and xi in terms of the x can be written as 1 minus 2 times x1 by x. So, as x tends to infinity, xi tends to +1, and then in general we can say that this has 1 over 1 by r times dk, because our distance is increasing in the ratio of this the singularity is in the denominator 1 minus xi. So, as xi is tending towards 1, we are reaching the infinite distance in proportion to this denominator value. So, our coordinates x1 and x2 are entirely user choices. So, x2 is normally we take as 2 times the x1, so that we get this relation that xi is 1 minus 2 times x1 by x. And we can actually, there are other forms of singularity I have not explained here, but you can refer to published papers. There are several papers, and I have referred to them in the list, and you will see the shape functions derived, or sorry, the mapping functions derived for other types of singularity, 1 by xi, or 1 by square root of 1 minus xi, or in the denominator you may have 1 minus xi square, and so on. You can see them from the published papers. And whatever we derived for 1 dimensions, we can also extend to the 2 dimensions very easily by using our Lagrange method. Let us imagine an 8 node quadrilateral with the 3 nodes 6, 7 and 8 at infinite distance. Let us define an 8 node quadrilateral like this. Node 1 and node 2 are finitely located, and these are the 2 corner nodes, and nodes 3, 4 and 5, these are the mid side nodes at different locations. Nodes 1, 2, 3 are at xi of -1, and nodes 4 and 5 are at xi of 0, and the nodes 6, 7, 8 are at xi of plus 1, and the xi of minus 1 refers to x1, xi of 0 refers to x2, and usually x2 is taken as 2 times x1. And we can imagine this mapped infinite element in 2 dimensions, and then write our shape functions and mapping functions. So let's look at, see, our mapping functions in the xi direction. They are developed in terms of the singularity at xi of plus 1. So our m1 is minus 2 xi by 1 minus xi, and m2 is 1 plus xi by 1 minus xi. Then in the eta direction, our along this line there are 3 nodes. So we have quadratic function in the eta, whereas along this line we have only linear function 1 minus eta by 2, 1 plus eta by 2, and by using our Lagrange method we can get our mapping functions in terms of xi and eta as the product of these 2 independent functions. So our m1 in terms of xi eta can be written as minus 2 xi by 1 minus xi multiplied by eta times eta plus 1 by 2. That is by looking at this. So in the xi direction, these 2 are our mapping functions. So in the xi direction, these 2 are our mapping functions. Then the eta direction, this is the one. So if you want for node 1, we can directly take a product of this and this, okay, to get our mapping function for node 1, and similarly for getting the mapping function at node 5, we will use this singular mapping function 1 plus xi by 1 minus xi multiply with this to get our mapping function at node 5. Let me turn it off. So by using the Lagrange principle, we can get our 5 mapping functions like this, and I want you to notice that we have numbered these nodes in an anti-clockwise direction. Unless you number the nodes in the anti-clockwise direction, you will not get your positive Jacobian matrix or the Jacobian determinant. So 1, 2, 3, 4, 5, and as the convention, we numbered the corner nodes first and then the mid-side nodes later. So 1 and 2 and 3 along the direction of 1 and 2, and then the 4 and 5. Okay. And although we got these mapping functions directly by using the Lagrange method, we see that our sigma of mi is exactly equal to 1, and actually that is very simple to notice, because the mi's are 1 at their own nodes. So this the shape function m1 is 1 at this point, xi of minus 1 and eta of plus 1, and at this point your m3 is 1, and if you evaluate m3 at any other points, it is going to be 0, and so on. Okay. So our sigma of mi is exactly equal to 1. That means that we can expect unique mapping between the Cartesian space and then the isoparametric space. So now let us look at the shape functions for the infinite elements. And the infinite element I have considered only 5 nodes out of the 8 nodes, and the other 3 nodes are at infinite distance. So our the shape functions we can get by the the progressive correction methods that we had seen earlier. So, our N3 is 1 minus xi by 2 times 1 minus eta square. In the eta direction we have 3 nodes, and along the xi direction there are only 2 nodes. N4 is 1 minus xi square because there are 3 nodes in the xi direction. Then in the eta direction there are only 2 nodes, so 1 minus eta by 2. N5 is 1 minus xi square, 1 plus eta by 2, and N1 for the 4 node element. See, for the 4 node So, the shape function for the 4 node element is this, and the correction because of this mid side node along this line 1 2 and along that line the horizontal line at 1 at 5. So, this is the N1 4. I can write it as N1 for the 4 node element minus N3 by 2 because we have defined one mid side node in this line, then N5 by 2 because we defined another mid side node along the horizontal line, and then similarly N2 is N2 for the 4 node element minus N3 by 2 minus N4 by 2, and then we have the 3 other shape functions for nodes 6, 7, 8, but we do not bother about them because anyway we are not going to use them for interpolation because the displacements and then the pore pressures are 0 at these at that far off location. So, let me go back to the laser pointer. Okay. So, how do we do the computations? Is very simple. Our stiffness matrix is written as integral B transpose dB integrated over the volume, and as we had seen with the other continuum elements, we can write the K as a double summation over xi and eta B transpose dB multiplied by Wi times Wj. These are the weight factors in the xi and eta directions multiplied by this determinant of the Jacobian matrix and the factor. The factor is 1 for the plane strain and the thickness for the plane stress, and then the radius for the axisymmetric problems. For example, for plane strain element, this B matrix will be of 3 by 10 for the 5 node semi-infinite element or the mapped infinite element, 4 by 10 for the axisymmetric problems, and the stiffness matrix will be a 10 by 10 matrix for the 2D problems for the 5 node infinite element. Now, our Jacobian matrix is formulated using our singular mapping functions. So, when you calculate dou n by dou x, dou n by dou y and so on, we use the mapping functions because we need this dou x by dou xi, dou y by dou xi and so on. And so, by using the mapping functions, the singular mapping functions, we can get our infinity into the calculations. Then our stiffness matrix is formulated using our regular numerical integrations, and for the infinite elements we use a 2 by 2 integration, lower order of integration, whereas we use 3 by 3 for the finite elements. And we should not apply any external loading on the infinite elements, because if you apply any external loading, either a uniform pressure or a concentrated load, that means that your loading is applied up to infinite distance, because our infinite elements are basically representing a semi-infinite length. So, we should not be applying any external loading, and similarly self weight should not be assigned to the infinite elements, because basically these infinite elements, they are representing infinite soil volume, and if you define any unit weight, you will see some peculiar results, because your gravity forces will be so high that your displacements will be very, very large. And other precaution that we need to take is, we should not allow any failure to take place within the infinite element. So, if any plastic failure takes place, that means that up to the soil up to some infinite distance has failed. That is not the reality, because our applied load on the surface may be spread over some time, some distance, like 3 to 4 times or 3 to 5 times the footing width, and beyond that the pressure is so small that you cannot have any failure. Okay. So, we make sure that all the infinite elements, they are assigned only linear elastic properties, so that you will not have any failure. So, we should not do this, like you cannot apply any uniform pressure all through, because this is not a finite distance, this is actually infinite distance, because this is part of an infinite element. And you see here, actually this is our finite domain, the elements represented by finite elements, and then these are the infinite elements. So, 5 node infinite elements. Then along this direction we have infinity in one direction, whereas at the corner we should technically have an infinite element that has the infinity in both xi and eta directions. But by experience it is seen that by just simply moving the this line at 45 degrees, we can by using our one dimensional mapped infinite elements, we should be able to represent 2-dimensional infinity. See here, if the local direction will be something like this, and for this the local direction is something like this, and that shows that you have infinity in both xi and eta directions. And the other precaution is, we should not activate any self weight on the infinite elements. Is also very important, because these infinite elements, they represent infinite volume, and your loading on the infinite elements means you will have tremendous loads in the load vector. So, the use of the mapped infinite elements is very simple. The infinite elements are joined to regular finite elements at some distance, so that our semi-infinite nature of the soil can be represented. And the region of the soil where the response under the loads is critical is meshed using finite elements. Normally the predominant influence of any applied load on the surface is felt up to some 2 to 3 times the footing diameter, or say even 5 times the footing size, and within that domain you can have normal finite elements, and beyond that you can place your infinite elements. And in the plasticity problems, infinite elements are connected at sufficient far off distance that we can directly assign linear elastic properties for the infinite elements, so that there is no failure. So, the accuracy we can easily check, because we have number of theory of elasticity solutions for the loading on the surface of an infinite soil domain. The circular strip footing, the circular loading on a circular footing, or a continuous loading, strip loading on a wall footing, and so on. We can compare our numerical results with these theoretical solutions for verifying our accuracy. So, here we have two meshes. One is a purely a conventional mesh with finite elements, whereas the other one is called as a coupled analysis, where you have some finite elements, or where you have a region with finite elements and then another region with infinite elements. And let us say that we connect the infinite elements at a distance of beta times the radius of the footing or half width of the footing. And this is one typical finite element, where your footing is here, and then but your domain is very large. Okay. And this is our pressure distribution along the central axis, along the this is the surface settlement bowl, and this is the vertical pressure variation along the symmetry plane, symmetry axis. And we can do the same thing by connecting infinite elements at different distances. So, in this case the infinite elements are connected at 1.5 times the footing width, and when we use finite elements, we should be careful about the boundary conditions. So, on both the sides we have supported the vertical surface on smooth rollers, whereas at the bottom surface both x and y direction displacements are constrained by connecting hinges to all these nodes. Basically, that is to represent a rough rigid surface, and the two vertical surfaces are treated as a smooth rigid boundaries. Whereas with infinite elements, we enforce only the boundary condition corresponding to the symmetry and nothing else. And in fact, if you do the same thing with finite elements and try to solve, you will have a singularity problem. The program will complain that your stiffness matrix, one of the diagonal terms is 0, because there are not enough number of constraints in the case of finite element analysis. But then in the case of infinite elements, there is another node at an infinite distance where we are saying that your displacement is 0, and so technically speaking, this is like this mesh with these boundary conditions is representing a very large mesh with the 0 displacement at infinite distance. So, because of that you will be able to solve, and this is our deformed mesh when we connect the infinite elements at 1.5 times the footing width. And we can also use combination of quadrilaterals and triangles. So, here I have drawn some radial lines for representing your infinite distance, and we can compare our finite element results with the corresponding theory of elasticity solutions. This is the maximum settlement at the center of a bowl, center of a flexible circular footing, and this is the settlement at the edge of the footing, and these are the stresses along the z axis, sigma z, then sigma r, sigma theta, and so on. Okay. And the conventional method is with the regular finite elements, where the boundary is placed at 2 times the footing width, 5 times, 40 times, and so on. Then in the coupled methods, 1.5, 2, 3, and so on. And in all the cases, the coupled methods with finite and infinite elements, they have much lower number of elements and degrees of freedom. And here is a plot between the remoteness factor, that is the distance up to the boundary in the case of finite elements, or the distance where the infinite elements are coupled with the regular finite elements, and on the y axis we have the error, and this line is corresponding to coupled analysis, where you have used both finite and infinite elements, and the percentage error is very small, of the order of 1%, whereas with conventional finite element analysis, even when you join the when you put boundary restraint at 20 times the footing width, there is still about 5% error in the displacement that you predict, or if you locate them at 5 times, then your displacements have an error of 15%, and if you have 15% error in displacements, your stresses will be will not be or will have more error, like might have about 25 or 30% error. So, we will not be able to even maintain the equilibrium between the applied loads and then the reaction forces. This is the settlement bowl. This dark line is the analytical solution, and this is our coupled analysis, and this is with this is with beta of 2, and this is the conventional analysis with a beta of 10. There is still so much variation between the theoretical result and then the finite element result when we use our conventional analysis, where we fix the boundaries at 10 times the footing width. Whereas with infinite elements, even when you couple at a distance of 2 times the footing width, the result is very close to the exact analytical solution, and we can verify our results even for a strip footing, and the solution for a strip footing are given in terms of the depth to the hard strata. So, let us say that the d is the depth to the hard stratum, and this is our equation for settlements, W within the for a point within the footing, and the settlement equation for a point surface point outside the footing. And once again, a very small number of elements and degrees of freedom were required in the case of infinite elements, and so these are the results with conventional finite elements. When you place the boundary at 10 times, if you back predict, it is coming to about 12, and with the 20 it is coming to 23, and with 40 it is coming to about 44. That is, we can back predict to get back our analytical result, and so with finite element analysis there is no benefit, because if you place the boundary at 10 times the footing width, then you get the results only corresponding to that. But then if you use a coupled method, if you place the boundary at 2 times the footing width is equal to placing the boundary at about 40 times the footing width, and if you place it at 5 times, if you place the infinite elements at 5 times the footing width, is equivalent to fixing the boundary at 103 times the footing width. So, it is actually a very huge difference between the finite element and infinite elements, and the advantage with infinite elements is we use a lesser number of elements and lesser number of nodes or degrees of freedom. So, our solution is going to be faster, especially if you are solving any nonlinear problem or the dynamics problems. The solution times are the order of say in terms of days, 24 hours or 1 day or 1 week and so on. So, here you see the comparison between the analytical and then this finite element solutions. So, this is for a beta of 2. The d by b comes out about 41, whereas for finite element analysis the d by b is about 12, although the boundary is fixed at 10 times, there is a slight difference. It is not coming out exactly as 10 because of the numerical errors, and these are the predicted stresses. The black lines are the analytical stresses, and then the dashed lines are from different finite element analysis. And you can do the same thing even with pile foundations, and especially when you have very long pile foundation, it's hard to decide where you need to keep your boundary, because the pile length itself is it could be 30 to 40 meters, and beyond that how much soil we need to place, either 1 times, 2 times, half a time, and so on. And so in the analysis, finite element analysis of piles usually involves in very huge meshes. So if we can save on the size of the problem by using intelligently using this infinite elements, then we can have much faster solutions. And similar to what we found with the surface footings, the percentage error with finite elements or infinite elements is very small, of the order of about 1 to 2%, whereas with finite elements there is a huge order. Even with say 10 times the footing width, your percentage error is about close to 4%. But if you use a length of mesh 5 times the pile length, you will get you will still get a very large error. So just to summarize, the use of infinite elements for some geomechanics problems is demonstrated. We have seen for footing problems, circular footing, and then the wall footing, or a strip footing, and then we have seen for pile foundations. And the mapped infinite elements are very similar to our isoparametric elements, except that they have singularity in their mapping functions, and they are highly accurate. And these mapped functions that we have discussed, they are implemented in some programs like Abacus and NPTEL-NOC. Abacus is a very good commercial program that is used by not only civil engineers, by mechanical engineers, electrical, chemical engineers, everybody. NPTEL-NOC is another geotechnical specific program that also can be used for several things. And in the Abacus manual, they recommend the use of infinite elements for all the in place of our viscous boundaries, because they usually give better results. That we will see later. I will show you one example that was obtained with viscous boundary and then with these infinite elements. Okay. So that's the end of my lecture. So if you have any questions, please send an email to this address, profkrg@gmail.com. Okay. So thank you very much.